We found that no cancer cell that we have ever looked at or anyone has ever described can survive on ketone bodies or fatty acids in the absence of glucose and glutamine. So when you know that, what I just said, you now know the strategy for managing the vast majority of cancers without toxicity.
All right, well, a couple of questions here. So I guess normal cells will do oxidative phosphorylation. They use oxygen to produce ATP. What is this fermentation process? What inputs does it use? How efficient is it compared to OXPHOS? Give me some details on it if you can.
Yeah, well, fermentation is the most ancient pathway of energy metabolism. It's an heirloom of the past. When organisms first arose on the earth, I think it was about 2.7 billion years ago, there was no oxygen in the atmosphere. So all the organisms at that time used a fermentation mechanism. Fermentation is simply energy without oxygen. And the glycolysis pathway is one of the most ancient pathways known. It's the pathway of life. After cyanobacteria produced oxygen, then we came to eukaryotic and more complicated metazoan organisms. So all of the cells in our body have this glycolytic pathway that prepares glucose for full oxidation in the mitochondria. But the cells that evolved originally had no mitochondria and they didn't use oxygen. The cancer cells are simply falling back on these ancient pathways. So they now, in normal cells, the preparation of glucose for pyruvate is present in the majority of our normal cells. And then the pyruvate is fully oxidized in the mitochondria using oxygen, generating a large amount of energy. But the cancer cells can't do that. They grow without oxygen, and they upregulate these ancient fermentation pathways, which involve fermentation of an amino acid, which is glutamine, and the fermentation of the sugar glucose. So these two fuels can be fermented, generating energy without oxygen. So clearly,
quick question here. I don't know if this is a chicken and egg type thing. Do cancer cells start using fermentation pathways because they end up being in an anoxic or low oxygen environment, being inside a solid tumor, let's say, no vascularization near them? Or do they first start doing this pathway and that allows them to continue to exist in a low oxygen environment?
Yeah, both. So, because that was the whole thing that Warburg showed. He showed that cancer cells continue to ferment even in 100% oxygen. So why would a cell continue to ferment in 100? We're in 21% in our atmosphere. He grew cells in 100% oxygen, and yet they were still throwing out large amounts of lactic acid. So they're doing that because their mitochondria is defective and damaged in number, structure, and function. I went through the ultrastructure of all the major cancers, so I had to go back in the 60s and 70s and find papers showing the electron micrograph of mitochondria. And you look at the mitochondria and you find them to be few in number, and the cristae, the inner membrane enfolding is abnormal, vacuolizations, they have all kinds of defects. Structure determines function. It's a foundational principle in evolutionary biology. So if the structure of the organelle is abnormal, the function of that organelle will be abnormal or insufficient. So some cancer cells may use oxygen for production of some ATP, but it's neither necessary nor sufficient to keep them alive or growing. So they have to have a fermentation metabolism in order to remain alive and grow. And that's what all the cancer cells seem to share, that common pathophysiological problem. They can't generate sufficient energy from oxidative phosphorylation. Therefore, they must ferment to stay alive. And the organelle that controls the cell cycle, allowing cells to grow in a regulated way, is the mitochondrion. So if the mitochondrion is defective in number, structure, and function, the cell loses control over its differentiated state and falls back on its default state, which is proliferation, as was shown by Dr. Sonnenschein and Soto from Tufts University. Proliferation is the default state of the metazoan cell, and the default state of energy is fermentation. So these cancer cells are doing nothing more than falling back on these ancient fermentation pathways, allowing them to grow. And as long as they have availability of glucose and glutamine in the microenvironment, they're going to be hard to kill. The problem is most of the treatments that we use today don't specifically target their fermentable fuels.
All right. So, keto diets and things like that, people can massively reduce glucose. What happens if you're reducing glucose, but I would think glutamine would be very difficult to reduce? What happens to cancer if, again, in a very low glucose environment that relies on fermentation? Will it just use glutamine and that's plenty enough fuel for it?
They can hang on with glutamine, but they can't really grow without glucose. You need the glucose carbons as fuel for metabolites, the synthesis of lipids and proteins and things like DNA and RNA. But there's no diet that will lower glutamine down. Water-only fasting for, maybe 2 to 3 weeks can lower glutamine, as was shown by the late George Cahill, president of the Joslin Diabetes Center. But we use drugs like 6-deoxynoreleucine, DON. This will shut down the glutaminase, so glutamine to glutamate is inhibited. And you can shut down glutamine pathway pretty effectively using drugs, especially when the patient or the preclinical system is in nutritional ketosis. So you lower blood sugar, and then you target glutamine with specific glutaminase targeting drugs and elevate ketones. So all the normal cells of the body, including the brain, switch to ketone metabolism, and the liver, of course, will burn fatty acids. Cancer cells cannot live on fatty acids or ketone bodies in the absence of glucose and glutamine. So they become non-fuels. They're fuels for normal cells, but not for the tumor cells.